Well, welcome to the department seminar for today. And I want to tell you, my name is Alan Hoffman, and the reason that I'm introducing the speaker is because if our chairman, Professor Youngmin Kim, introduced him, you'd get very confused because he's another Kim, our speaker is. So I'm going to clarify who's who here. It's a very big job. In fact, I could take half of his time just introducing him because his accomplishments are so enormous. Seung-Won Kim, who is probably, in my mind, my little brother, he's a very, very close friend, is currently Distinguished Professor of Pharmaceutics and Pharmaceutical Chemistry, and Adjunct Professor of Bioengineering, and Director of the Center for Controlled Chemical Delivery at the University of Utah. He got his BS, MS at Seoul University, Seoul National University, which is the top university in Korea. His PhD came from the University of Utah in 1969 under Professor Henry Eyring, and many of you know about activation energies, and that was his professor. He's a pioneer. He's a pioneer in drug delivery research. He's a pioneer in biomaterials. He's made huge contributions, original contributions, in almost any field related to biomaterials. And I can tell you this because every time I think I do something novel and new, and I start looking into the literature, I find his name there. So he's always come there before almost everybody. And for this kind of pioneering contributions, he's been recognized by every major professional society in our field with their major awards. He's received the Dale Worcester Award of the American Association of Pharmaceutical Scientists, which is their top award, the Controlled Release Society Founders Award, the Biomaterial Society Clemson Award for Basic Research, and I could go on, but I don't want to take a lot of his time. I do want to say one thing, it's very important. He is not only an outstanding professor, he has received the Utah Governor's Medal of Science, he's received the University of Utah Distinguished Research Award, he is a member of the National Academy of Sciences, and it's my great pleasure to introduce Seung-Won Kim. Seung-Won, let's welcome Seung-Won Kim.
It's my great pleasure to be on this campus. This is actually at least about 5-6 times I visited this campus. My first visit is 1972. Alan moved from MIT to this campus. Then I visited here. Then Alan tried to get me here. I wanted to come here. However, it didn't work out. I decided to stay at the University of Utah. I spent a little time with Dr. Youngmin Kim this morning. Then University of Washington and your bioengineering department, of course, is, in my view, is the top or one of the top. So I'm very happy to see your faculty and the graduate student here. Then Alan and I shared a friendship. We call it almost lifetime. So he helped so much. Then he mentioned to me always I am ahead of him. It's because I learn faster than he is, although he swims faster than me, yeah. And that's the only reason. That doesn't mean I did a better work than he did. Today, and I want to talk about, maybe the topic is biomaterials for gene delivery. One thing is, I saw in the two of my students, I think, and I joked them, but they are really here. They looking for a job around. Then I told them and come here, then apply a job today. And there's Horst van Neckum, who had a PhD with me, now MIT with Bob Langer. So I think he is applying job here. And Matt Lentz, who just finished the PhD last year. One guy is tissue engineering, the other fellow is gene delivery. So have you looked around all the campus? Okay, yeah, Matt and Horst there. So I think they listened my lecture first time, this 1 hour lecture. Gene delivery is here. Now, and let's see the in disease-wise, and most of the gene therapy clinical studies in cancer area, some in the rare disease, monogenic disease, infectious disease, and some cardiovascular and others. But more importantly here, the vectors, the gene carriers is adenovirus, retroviral, and naked, and now AAV is increasing now. But this, we belong to the others. Others is a very, very minority, is less than 1%, which is good, and it's always a percent is based on 100% relatively, but this will grow. Others is mainly polymer carrier. I bet you within 5 years, this will be increased at least 5–10%. This is the area now in my group is working. Next slide, please. Oh, I can use this. I'm not going to get in detail about the most popular and known, very well-known adenoviral gene carrier. At the beginning of gene therapy research, and then the problem was how to put the naked gene into the cell. Then all biologists failed 20 years ago. Finally, put the gene in adenovirus, and then perhaps we have several thousand papers in this area. This slide was given by Dr. Lou Messina, a famous vascular surgeon in the University of California, San Francisco. Actually, he is the pioneer of adenovirus gene. This is his slide, his work. He tried to treat and rabbit the rat, actually here, the hindering ischemia using adenoviral gene carrier and using enos gene. Then, and about 60% of his animals show this black leg. Is mainly due to the inflammatory response here, you know. So he is almost giving up using adenovirus. Quickly then, and I use this slide, and Jim Wilson, who is in the Seattle now, and he gives a lecture today at the convention center. Then this is, I made a copy of this from Science last September. He tried to treat the patient, and the patient, the young man has a liver ornithine transcarbamylase. We call it OTC deficient patient. Treat the patient with adenovirus carrier. Then it's died of immune response, and FDA shut down, and the laboratory, I mean clinical center. Then, and some people use and naked gene, and Jeff Eisner give talk tonight, and I'm going his presentation tonight. Then his patient died. He used VESAP gene and huge amount of gene, naked gene, to treat and myocardial infarction, MI patient. Patient died of cancer because he didn't know his patient has cancer and the tumor. Then VESAP and stimulate the tumor cell, you know. Then, and now then we have to justify why non-viral gene carrier. And then, and we can design in the many carrier, which means it's good for producing new PhDs, you know. If we have new idea, new design, is one PhD can be produced. And the non-infectious, non-immunogenicity, this is very important. No integration into host chromosome, very low toxicity, and we can do a continuous injection. Then this is a very important conventional route of administration. I'll explain this later. High patient compliance. Then this is this is very exciting and a new area. Then quickly I review, and then I show this slide 3 years ago when I came here. At the time, my presentation emphasized this just a few polymers and a few vitro experiments, and I promised the audience at the time within 3 years I will bring animal data, which I did today. Then this is a monofunctional, bifunctional, and then this polylysin. This and positively charged polymer, the function is condensing the plasmid DNA like this. And bifunctional, we add PG or target lactose. PG is this makes the carrier less toxic, less immunogenic. I sat down last night in the Gene Society meeting. I saw that some biologists mentioned about pegylation to reduce immunogenicity, and many people say, what is pegylation? That's the last night, and you all know why we use PG. Then this is a trifunctional target moiety PG and galactose and nuclear localized system, and then bifunctional, this way, and then all this, yeah. Then one of the trifunctional we have been working for years is there is LDL. This is LDL and has receptors, low density lipoprotein at the cardiovascular system. And then this is alkylated PLL, and the red is a gene like this. And then our research at the University of Utah, we are drug delivery group, and this is a very important part, and not many people thinking about this. And then how we are going to administer the gene delivery and the gene. Then we can divide these three. We can deliver gene systemic delivery, then local delivery, and the targeted polymeric carriers. Then we divide our carrier these three categories. Then I'm going to talk about polyaminobutyrate glycolic acid and the soluble degradable cation polymer systemic delivery of IL-4, IL-10 gene to treat diabetic insulitis treatment. Local delivery is intratumoral injection of gene and the polymer. We're using water-soluble lipopolymer and the lipoparticulate and the soluble steroidal peptide. It's working very well local. Then very interesting story is we conjugate targeting moiety like lactose, RGD. The RGD we are using is angiogenesis cell. There's receptor, Then arterial wall binding protein and the Terprex, and I'm going to show Terprex and AWBP for cardiovascular disease treatment, and then water-soluble lipopolymer for renal carcinoma treatment, and the PAGA is for autoimmune-induced diabetic treatment. Then this is the cartoon, and we've been working Terprex. I will explain you soon. Arterial wall binding peptide, I will describe you. Then in the water-soluble lipoprotein, this local delivery, IL-2, we constructing our own gene. In this case, we use the double promoter and produce much effective IL-12 gene. And then the disease is ischemic heart, hind limb ischemia, then and the renal carcinoma and the lung cancer for this. Then in the current status, in the 20 people worked in this area with the clinician very hard. We completed in the red experiment. Now we're doing rabbit myocardium animal model, and then animal model just initiated. This one is a mouse completed, and then this one is a feasibility completely done. Yeah. This PAGA and IL-4, IL-10 and the chimeric gene and insulitis, diabetes, and NOD mice studies completed. This one is we haven't done much. And then lactose, PGPI, and as you know, factor VIII is produced in the hepatocyte, the liver. So we deliver this gene carrier, factor VIII gene, using lactose targeting in the animal in the liver. Then this is for hemophilia treatment. And then we have RGD, PG, PAI, then and this RGD go to alpha integrin, anti-angiogenesis cancer treatment in vitro is completed, and this is new and we just started. And then this is the all the steps we're doing in our laboratory, and we establish this, all the facility and the instrument and the procedure in the lab can be done routinely. That's with the functional and the targeting polymeric gene carrier. And we design a systemic local site-specific gene delivery I mentioned to you, and the synthesis and the characterization, we see toxicity very quickly, and we try to verify the mechanism here, endocytosis, endosome, and the nuclear transfection, transcription, translation. And the fate of polymer is very important. We're using biodegradable polymer. Then the most important is two, and we always think animal model for specific disease, and we select the cell in vitro. And then in the first, and I want to describe in the two gene carrier system for cardiovascular disease treatment and target specific gene delivery. Then this is the Terplex DNA, and DNA, and we have, I showed you, cationic polymer, sterile, and mixed with LDL. Then LDL and has strong hydrophobic interaction with alkyl group. Then this positive charge in DNA is condensed like this. This is we call Terplex DNA to target cardiovascular system. Then this is one of the example of characterization. I don't have my name first. I seldom have. This is another Kim, Jinse Kim, my old postdoc who is in Korea now. Then we characterize and such as surface charge, then and the size, and then DNA protection assay. Then we see this way, and the linear open circle and the supercoil, and we measure, of course, zeta potential. All of them published in these papers. By the way, I brought in our publication list the last 3 years. Then I will leave that copy to Dr. Hoffman. I will leave it with Alan. If you are interested, go to Alan's office and get the copy from him. I brought one. It's in my bag in your office. I will leave it with you. Yeah. Then also pharmacokinetic and biodistribution. Whenever we design new carrier, we see the carrier, pure carrier, and then DNA complex. This is the example, naked DNA and Terplex DNA, how it's different. Naked DNA half-life is 1.96, is 6 hours. Then clearance 0.13, MRT is 2.5. Then elimination clearance, mean residual time, and steady state volume of distribution is a big change, you know. This is, we obtain this data occasionally, yeah. Then this is the toxicity study. We are doing MTT and cell viability studies, and naked DNA, Terplex DNA, then this transfectamine. Transfectamine is a commercially available cationic polymer. Cell died, you know, here, and about 60% cell died, and then this and the purple naked, and then our Terplex DNA, when we use and 0.05, 0.5, and no toxicity at all. If we use 1 microgram, it starts to show toxicity, you know. This is all the data, and then this is the transfection Terplex DNA modified gene transfer to vascular smooth muscle cell. Then this is the transfection using marker cell, then this is not, you cannot see very well, but the story is Terplex DNA using and the marker gene showed very high transfection into the both cell and the smooth muscle cell and the endothelial cells. Here, and we're using primary cells. Then this Vitro study showed us Terplex are very effective in the carrying the gene, and then transfection and translation, etc. Then in this, and we have done a lot of work this, and then this is a summary. As I mentioned to you, DNA Terplex is very high, and the cell specific, and muscle cell, and the endothelial cell, and the Terplex is a very stable serum and the PNAs. Then, and we know that this leads specificity of LDL facilitates internalization of DNA into the cell. Then, and this is also the enzyme protective effect, and then long half-life, and the result demonstrate the advantage of Terplex system for in vivo operation to the high bioavailability in the tissue. This means cardiac tissue, yeah. Okay, then, and now, and we're working with the cardiovascular surgeon group, Dr. Dave Bull group at the University of Utah. Then, and they are very excited about this carrier. Then this is ischemic heart disease, and this is long, and 200,000 patients. Then, and now that there are some treatment, and then it's a problem by stimulating local inflammation, promoting cancer growth, and then using naked gene, VESAP, such as VESAP. Then this VESAP, we use naked gene. We have to give very large amount. Then this VESAP gene distribute all over the body. I showed you the worst case, one cancer patient died. Then, and we injected and Terplex, and this already published, and this old slide, this naked gene, and then this is light is a little bit here, but we injected and the site of impact site, and is huge, and a very large amount of gene was transfected, and then this Terplex is working very well. This published in a few months ago in the gene therapy. It's color picture. Then, and this is the luciferase activity and the marker gene. You see here Terplex and gene, and luciferase production is like the 50,000, 60,000, compare only few hundred of the control. This is the naked gene, So we injected it the Vivo rabbit myocardium site, specific site. Then, in the gene transfer here, this is very important in the kinetics. How often we have to give the gene injection. Then Terplex is here. The naked is here. It is by one injection. It's protein production in the myocardium, gene expression with time course. This we have this kinetic data. This kind of data is very important to carry in the human. Then this is a very important data which I never thought. This is a cardiac surgeon always think, and the ejection fraction of pre-ischemia, and then treatment and the control, it should be very similar. Then we are very fortunate, and N mode and 2D mode, and is all same, which means that we can give it to the patient. The carrier and the gene, we can give it to the patient. This acute myocardial infarction model. Yeah. Okay. Then, and let's change the topic a little bit. At the beginning, I mentioned about the site-specific, and that's all the LDL specific targeting work. And we have arterial wall specific targeting and artery, and then we can design arterial wall binding peptide ApoB100. Next I will show you the peptide 2 and the PLL, PEG, and then this black is targeting modality, or even we can put the SB40 NLS nuclear localizing system peptide there and plasmid, and it will go here. Okay. Then in the arterial wall and the myocardium binding domain, the LDL we used, and I mentioned about it's not necessary we have to use LDL. We can use real important part is ApoB100. In the ApoB100, and also the more important thing is that this peptide, real binding site is here. Then now we're using ApoB100 and also peptide is amino acid 16 sequence peptide. Then here is arterial wall binding. This is the we use now the polyethylene imine for endosomal disrupting function, and the spacer PG 3000, and we use the peptide or ApoB100 is both working very well as well. Then this is arterial wall binding peptide PG-PLL mediated aorta endothelial cell gene transfer. As you see here, arterial wall binding peptide conjugated PG cationic polymer show very high and transfection. Then this is the concentration. This is smooth muscle cell and the endothelial cell, and both arterial wall binding peptide and PG-PLL is working and very well. A specific targeting modality next, and PG and the PLL. Then now we design it, instead of PLL we use the PI polyethylene imine, which has tertiary amine, which show the abrupt endosomal disruption. This is all we design, and this we use in the primary cell here. Then this is inhibition of transfection assay. It's very important, and it's very specific binding or not, and we add free arterial wall binding peptide, and then we show here as the concentration of free peptide increase, its transfection decrease because free peptide and occupy the receptors. Then we do this kind of things to verify the real mechanism. Okay, now and then gene delivery people, like as I did the last few years, all think about the design of carriers. Then last 1 year, I studied in the more biology, and I learned more about the gene. Then why then we have to use existing gene alone? Then why don't we modify it to make the genes more effective? Then I brought a couple molecular cell biologists over a year ago, who has many years experience constructing the plasmid DNA. Then we got in this area. Now we are discussing for clinical study for myocardial impact. Then I talked to surgeons. They say, and if the amount of VESAP is too much, then we may have problem. Then I told him, first of all, the dose we are using is very small. It's by injection and the site and the specific targeting, and we have animal data. Distribution in all the organ is very small. It's localized in the cardiac site. Then we use in the VESAP gene. If any problem, let's use a mini dose of heparin. Then those who have a VESAP gene patient have a mini dose heparin. Then we knock off circulating excessive VEGF. They like it very much. Then we agreed to do it, like 1,000 units per day. And the second, why we use and we modify VEGF gene, then have a large amount of protein is produced, and same amount if we design specially functional gene. We have idea. The hypoxia, let's make a hypoxia gene. Hypoxia gene concept is not new, and some people use cancer or some place, but we decided to construct our own gene, hypoxia gene, with our carrier. Then, as you know, the impact site, ischemic, myocardial ischemia, is lack of oxygen. It's much low oxygen than venous side. Then we studied the ODD gene, which are available H1, F1, and alpha unit and beta subunit and oxygen in this way. Then the idea is here. I brought in the very simple idea. This is existing VEGF gene we are using. We introduce ODD gene. Then in the normal tissue, rapid degradation, but the ischemic tissue, and this is very stable, you know. So we decided to construct this gene we call VEGF ODD combined gene, you know. Then use CTRT promoter and the VEGF ODD gene, and then now we carrying animal studies, and then we now checking all the produced VEGF in other organs, in circulating blood, and we'll have this all final data soon. It's very promising using this kind of gene, you know. Okay, that's the conclusion of specific targeting. I gave you example. We will move in the clinical study by the end of next year. Your first system is using Terplex, and the gene is a VEGF gene with heparin together. And the second approach is using ODD gene and our carrier, and without using heparin. Then our ODD gene is very good. The final product and the protein, produced protein VEGF is exact same as the VEGF which FDA approved now, VEGF, you know. So we'll have two approaches, and the decision will be made by surgeons now. And we have extensive animal study with the rabbit, and then I didn't bring all recent data. It's promising. Next, and I'm moving to local delivery of therapeutic plasmid DNA, local, not specific targeting. Then cationic lipid is very well known on gene delivery. However, this cationic lipid is toxic, and there are a lot of problems here. Then it's reviewed by Mahado, who is my associate now, cationic linker group and hydrophobic lipid, TOTMA, and this, you know this very well. Then we are making cationic cholesterol grafted PI. Then PI 25,000 is very effective, but the molecular weight over 25,000 is very toxic. Then we decided to use the small molecular weight PI, which is water soluble, which are non-toxic at all, but transfection is too low. Then we decided to combine it with cholesterol. Then cholesterol and lipopolymer condensed DNA by both electrostatic and hydrophobic interaction. The lipid, you know, we use cholesterol coating on DNA, increases permeability to the cell membrane. This is the idea. Then this work and water-soluble lipoprotein, we receiving the best scientific award tomorrow at American Society in Therapy annual meeting. Is this work, you know. Han is my graduate student. Actually, he is receiving the award tomorrow with $1,000. Yeah. This is the low molecular weight PI, then cholesterol, and then 47% cholesterol conjugate to PI molecular weight 2,000 or less. Non-toxic, water-soluble cholesterol. Yeah. Then we constructed new gene. We introduced two cDNA, P35, P40. Then this and two cDNA compared to one P35, about 5 times more potent. We constructed this gene in our laboratory. Then, and this is all characterization, particle size and zeta potential and the complex. This is a routine picture, then atomic force microscopy, and we verified that it's well and condensed soluble lipopolymer pDNA complex and MPa of 10. The size is here. Okay, yeah, atomic force microscopic picture, yeah. Then this is toxicity is very important. The control is here. Then our WSLP, this is a PI 1800 even show toxicity. Our WSLP pDNA is non-toxic at all. This is very good. Its toxicity is none by MTD test. That's very important, this toxicity studies. Then this is erythrocytes, and then PI alone caused the erythrocyte cell precipitation. Our WSLP is none. Yeah, we're doing a lot of this kind of characterization. Okay, this is the transfection of WSLP, then interleukin-12 gene. Then here, you know, the amount of IL-12 production in the picogram per milliliter. This is for 24 hours, and you see here, this is all and very high. The naked gene is here. It's very good, and the 25 composition NP, you know, here white, you know. So then, and this is a very good 25, yeah. So we can use this, any of these 15, 20, 25, 30, and the ratio NP. Then this is again the interleukin-12 study, structure of molecular weight, and then here is, and the PI alone is very low, and then here is, you see that the WSLP and the interleukin-12 gene transfection is this. This is very high, yeah. Then this all control is very low. The animal study, we use, and the tumor is colon cancer cell, and inoculate in the back, RBC mice. Then, and we use ELISA for check, and then 48 hours post injection. The data I'm showing you now is not the curing data. We're doing curing data now in the 1 month, 2 months, 3 months. The data is more like expression data. Then in the, we express the intratumoral is a local delivery, I mentioned to you. IL-12 production, WSLP with this gene is very high. This is a control, and then this 24 hours, you know, it's very high. Then we did a lot of work with other carrier, and this the shrinkage or knock off the tumor cell depending on IL-12 production. Then simultaneously we measure nitric oxide and the gamma interferon, then all possible cytokines, and even we analyze and natural tumor killing cell, and then many cells we assay to Th1, Th2. This is one of the slides, just see the production of interleukin-12 in intratumoral in 1 day, you know. So this is the initial indication of the treatment of tumor, you know. So we're doing animal studies for several weeks, and then to measure size of tumor and measure the all cytokine level, intratumoral, and then all organ distribution. In local delivery, we want, and majority of activity should be done in intratumoral level, not in the blood, circulating blood or lung, other place, which our hypothesis is working very well. Then this is the gamma interferon, and I mentioned you, gamma interferon is a very important cytokine to knock off the tumor cell, and this is the one, yeah. Very nice data, yeah. The conclusion is transfection efficiency of WS water-soluble lipopolymer DNA complex, plasmid DNA complex was higher than that of PI alone. And in both in the Vitro and the Vivo, we're doing now long-term animal studies, you know. Size is 50 nanometer. Okay, my last few slides, and now in the systemic gene delivery, we give the gene carrier gene, the IV, bolus, you know, okay? In this case, and then gene carrier and the gene goes to any cells, such as a T cell. Wherever T cell exists, it's expressed the protein and we wish. Then this protein plasma level, we call this effective level. And we measure the protein level in the circulating blood. A certain number is we set effective. Then that protein is enough effective level to treat any disease. That's a typical systemic gene delivery. The pharmaceutical people, you take the drug orally or IV and intramuscular injection. We all measure the plasma level. We call BPL. A certain BPL level is effective level, above toxic, below in the non-effective level. That's what FDA guideline when we develop new drug. Then first two subjects and specific targeting, local delivery, and we try to minimize the systemic level. And then we want to see localized or targeted and the distribution to other organs minimum. That's what our approach. In this case, systemic gene delivery, we need effective plasma level by producing therapeutic protein. That's our approach, systemic gene delivery. To do that, we need a biodegradable polymer, of course. And this is, we synthesize polyaminopytyl glycolic acid. This is exactly look like a polylysine analog, but we have carbonyl degradable bond here. We say that PAGA is a degradable PLL. You know, polylysine, we worked with polylysine 25 years ago. Polylysine aggregate platelet is toxic. And at the time, then I checked 25 years ago, PLL degradation takes 3 years in body. Then if we accumulate the PLL in the tissue, eventually it's very toxic because it's stick on the tissue and with strong binding is not eliminated by kidney very well. And most cationic polymers are toxic. The reason is it's not eliminated quickly through kidney. Then we designed the degradable polylysine, which of course we expect is not toxic at all. Degradation is very quick. Then this is a comparison of PAG and polylysine. Polylysine backbone is amide, and then PAG is ester, is degradable, non-degradable, toxic, and non-toxic. Then we can give this, we can use the PAGA as systemic gene delivery carrier. Then we designed several studies. One of them is here. I brought a few slides to investigate whether PAGA can increase the transfection efficiency in the vitro. Then to investigate whether the systemic delivery of MIL-10 plasmid with the PAG complex can express the interleukin-10 protein and can prevent the development of insulitis in NOD mice, diabetic animals. Yeah, this is first and quick study, and we see the transfection. This is a control and no transfection. This is our PAGA and the marker gene. All the dots show the transfection, the same as a cationic polymer, PLL. This is actually more here, you know. Okay, then we found that PAGA makes the transfection. Then this is again the we have to select what kind of charge ratio we have to use, and 1 to plasmid PAGA 1 to 10 to 1 to 1 to 20. Then we select 5, 6, 7, 5, 1 to 5, 1 to 7, 1 to 10. This is a very stable complex, and then we use and the charge ratio 1 to 5, 1 to 7, and 1 to 10, and this plasmid and the PAGA when we design the complex, you know. Then this is again the cell viability. Polylysin is toxic, and the PAGA is non-toxic, and this is a control. Yeah, it's non-toxic at all. Then this is the IL-10 concentration picogram per milliliter. This is 293 T cell in vitro study. We do vitro first. Then as you see here, our carrier PAGA and the interleukin-10 gene, IL-2 PCA, GEG, S gene produced and 40 picogram per milliliter. And then control is here, naked gene, same amount. Then gene is here. This is a baseline. And then PLL is here. And then it's not much that our carrier is very good in the production of IL-10, which means a very large amount of gene was transfected. And then this is the animal study in NOD mice and IV injection. You see our complex 1 injection for 30 days, and it's maintained 30 picogram per milliliter. We established an effective plasma level from NOD mice study is 30 picogram. We need it, 30 picogram. The control is here in the dissipate and here very quickly. Then why it's 30 picogram, I'll show you next. And that amount of polymer, like 150 microgram polymer, about same amount of IL-12 gene, IL-10 gene, and we did the animal study. What is the, I didn't bring the all detailed slide. As you know, the cytokine related to cancer, such as IL-2, IL-12. I told you about IL-12 today is a Th1 cell. And then in the cytokine which are related to the autoimmune cytokines are IL-4 and IL-10 is this. Then in the normal and healthy human or mice, Th1 cell, Th2 cell is always balanced. This is pathogenic and protective. And then these cytokines have something to do cancer. This is autoimmune. And if pathogenic cell is too active, and then we have to give protective protein for balance to Th2 cell. And if we look the morphology of beta cell, this is an islet. Inside the pink is a beta cell. Most of you healthy human, I think most of you, the beta cell looks like this pink and cells inside. This is the progress of autoimmune insulitis is starting dark. And then when diabetic process is completed, become insulin dependent diabetic, this is all carbon black now. Then and this is the we see all this each stage of morphology and the color, evaluate the insulitis. This takes 20 weeks, this control, NOD mice 20 weeks, this, and within 3 weeks is still healthy. Then this is a suppression of insulitis in NOD mice. Then and this is our this is a control in the 8 weeks and the 12 weeks is 80%, over 80% animals have insulitis and by the beta cell morphology. Then and this is naked and DNA 1 injection it's worked until 6 weeks and then doesn't work. Then this is our PAGA DNA. Then it's almost in the Insulitis. Insulitis is prevented up to 8 weeks. Then we're doing and continually now. Then this is the week and we give a second injection. We can prevent and stop insulitis completely using the plasmid DNA, the concentration we set, and then the amount of gene carrier we set, one injection in the 12 weeks. Then we did all calculation, how much we have to give in human. As a pharmaceutic research, I have to define it. Then this the insulitis is prevented, and then the amount of plasma cytokine level to prevent insulitis, as I mentioned, that 30 picogram per milliliter plasma level. If we can maintain the patient plasma level 30 picogram per milliliter, and we can stop the insulitis, which is autoimmune induced diabetic progression. Yeah, this is all published in 6 months ago, and the gene therapy. Yeah. The conclusion for PAGA IL-2 gene, as I mentioned to you, and we produce and our own IL-10 gene now, and it's here. We use and combine the IL-4, IL-10 gene, and tomorrow my associate and endocrinologist present at the society meeting the chimeric gene, and we constructed IL-4, IL-10 chimeric gene, which show excellent for the prevention of insulitis. We designed in the new gene. Then now our animal study almost completed with a chimeric gene, and this is not chimeric gene story here. The next one is we designed IL-4, IL-10 chimeric gene and did in the 6 months animal study, showed in the suppression or total inhibition of autoimmune process which prevented diabetics here, and that's the conclusion. I think this is my next last slide. Then if I summarize my presentation today again, there's huge in the opening area of polymer carriers design. One of the benefits and we take advantage is we can produce and many nice and PhD by doing that. Adenovirus is very hard to produce good PhD. It may work in human, I don't know, clinicians, a lot of them working, but the FDA view is whatever the adenovirus, adeno-associated virus, lentivirus, many viruses coming out, there's non-toxic, non-inflammation. FDA view is virus is virus. Where the fragmentations goes, eventually the fate of virus fragment in body. That's everyday concern. That doesn't mean that area has no chance. There's still a lot of chance. Therefore, we see in the 1,000 paper a year still virus-related gene delivery. But now they are more cautious. Then polymer is non-toxic, non-immunogenic, it's versatile. We can design and many carriers like and for systemic, local, and the targeted is a very interesting area. Last night, and one lady presented work there. They have a phase display library. Then inject and series of peptides continuously with 1,000 animals. Then assay the animals, see where this peptide goes to find the receptors. There are a million receptors in our body. A huge area if student and design one cationic polymer and one peptide sequence conjugate and select a certain vitro cell and the Vivo animal model, that can be excellent PhD thesis. Then there's a wide opening area. Then next is many people ignored and forgot. It's not necessary we need always high transfection. When I submitted our paper until 2 years ago, human gene therapy rejected immediately one paragraph. Polymercaria will never work because transfection is too low. Then I challenged to Jim Wilson, the pioneer. We don't need high transfection many times. Look, drug. Do we need in the high dose of drug? And you have anti-hypertension pill. You take 10 milligram Rotensin. Do you want to take 100 milligram Rotensin to treat you, to care you better? It's none. It's toxic. It's same concept. As long as we have effective level, then as long as effective level, non-toxic, non-immunogenic, the minimum level is the better for the treatment. That's what I keep telling people. Therefore, is polymercaria, although transfections efficiency is much lower than viral beta, but it has wide open and good future. And then that's what I'm excited in this area. I'm crazy in this area. Thank you very much.